Alright, so today we do some important properties, and you'll see the importance of these as we move along. Here's the first one. The first one I like to call the limit of the sum is equal to the sum of the limits. Meaning that if you have the limit of a sum, that's the limit of a sum, it's the same as the sum of two different limits. Well, not different, but they're related to that function. Limit of the sum is the sum of the limits. So I use this little acronym for short to remember. And of course it has a little star here like the banks like to do on your credit card statements. It's a little disclaimer. And of course I made it super small so you can't read it. Just to be like the banks for fun, but actually you really need to read it. It is only true if each of these limits exist and is bounded. Now what in the world does that mean? That means that most of the time you're okay distributing this as you would expect it, but sometimes things could go really bad. By the way, I didn't put limit as x goes to what because it doesn't matter as long as it's the same thing. For example, if x goes to 3, well, it's got to be the same thing over here. X goes to 3, and it's got to be the same thing as x goes to 3 here. Or even -3 or 5 or 7 or infinity. As long as it's all the same, then it's not going to matter. So I think I can convey the principle without restricting myself to whatever limit as x goes to anything as long as it's the same thing. Anyways, let me give you a little tiny taste of that. Let's clone this page and then let's clear it. So for example, here's a famous example. Suppose you take the limit as x goes to 5 of 3x plus 4x squared. What that means is that I could take this limit and distribute it in there and distribute it in there and break it up into two smaller problems per se. This would be the limit as x goes to 5 of 3x plus a separate limit, the limit as x goes to 5 of 4x squared. So every once in a while you can do that. You could take this limit, which is the limit of two different functions, and you can break it up into smaller chunks, smaller problems, so to speak. And that works okay. For example, here I could do the plug-in method or whatever. This is 15 plus 5 times 5 is 25. So every once in a while that works, but now let me explain the disclaimer. Sometimes it doesn't work. Each limit must exist and it must be bounded. And what exactly does that mean? Let's clone this page and clear it. What that means is that, for example, suppose I had the limit as x goes to 0 of 1 over x plus ln of x. And you go on and you say, you know what? Hey, I had these problems. This is crazy. If I plug that in there, it doesn't exist. If I plug that in there, it's negative infinity. Something weird's going on. Maybe I'll break it up into smaller chunks, just like the limit of the sum. I'll try to play this game. The limit of the sum is equal to the sum of the limits property, and I'll break up my problem into easier chunks. And you say, okay, this is the limit as x goes to 0 of 1 over x plus the limit as x goes to 0 of ln of x. And then you might say, hey, I broke it up into easier chunks. What I'm trying to tell you is that this little disclaimer says, no. You cannot do that. You can only do that if does this piece exist? No. Does that piece exist? Forget about it. You can't be playing this game unless each of them exists, and each of them must be finite, must be bounded, which means you can't be infinity. This one right here doesn't even exist. This one over here is negative infinity. You got major issues here. It's not going to happen. And so if you do this, you're either a trailblazer or a lost soul. People who don't go by the rules, trailblazers or lost souls. This is trailblazer stuff or lost souls. Anyways, I hope that explains how you use the property. The limit is the sum of limits, but you've got this important disclaimer. It must be finite. Each of these limits must be finite. It must exist and be finite. Because sometimes they exist, but they go off to infinity, and then they're not finite. You got to have both things, exist and finite. Then you can play the game, okay? And then there's other ones that are super famous. You can imagine the limit of the product is a product of the limits. Same thing, you can distribute it to each of them. And of course you've got the all-important disclaimer. Each one must exist and be finite. Same thing with quotients. Limit of the quotient is the quotient of the limits. If you've got a fraction here, you could distribute it to each, the top and the bottom, and break it up into smaller chunks. Oh, but now you've got two disclaimers. Each of them must exist and be bounded, and you got an additional one. The bottom cannot be 0. If the bottom is 0, you can't play this game. For example, let me see if I can give you a really quick example of that one. Let's clone this page and let's clear it. Suppose I have the limit. Well, I'm not afraid. I'm going to do that. Limit of as x goes to 0 of 1 over, I don't know. Let me think. Let's go to infinity. 1 over x. Okay. So if you were to take the limit and distribute that, you'd get the limit of 1 on top, and you get the limit. That's crazy. Let me do that again. Let me go back to normal. I don't want to be a trailblazer today. The limit as x goes to 0, for example, of 1 over x. Could you play this game? Could you say, well, that's the limit of 1 as x goes to 0 all over the limit of as x goes to 0 of x. You say, well, okay, this one exists and it's finite, this one exists and it's finite, so no problem, right? No, 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 no. See, even though each one exists and is finite, you got another issue here. You got two disclaimers. Each one exists and is finite, but the bottom one cannot be 0. If the bottom one is 0, you're not using this property. You're a trailblazer or a lost soul. Okay? Here's a super famous one, the limit of x. The limit of x, you can imagine it, this function right here. Y is equal to x. So it's just a plain old function like that. And if you have some value c here, and as x approaches c, what do you think will happen to the y's? Well, they're going to approach c as well. That's sort of an obvious one by plug-in method. But it's an interesting idea to prove this one. By the way, these limit properties can be proven very, very rigorously, of course, with the epsilon delta definition. That's what makes it all happen. That's the intellectual backbone, sort of the mathematical rigor of all this is provided by the definition, epsilon delta definition. So this would, in fact, I've posted this on the homework. Prove this using epsilon deltas. It's a really important homework assignment, and you should check it out. Pulling a constant. So often you've got a function here, and you've got a constant coefficient on the function, and the idea is that you could take that constant, and whatever it may be, you could take it and pull it outside through the limit. Pull it outside, and of course you got two disclaimers. Each of these pieces must be real and finite. Okay, that piece right there, the limit must be finite and bounded, finite and real, and exist. And this one must be a real number. Of course, that means it's finite as well. All real numbers are finite and bounded. In other words, you can't be using where k is infinity or something that's not real necessarily. So maybe I could try a little example of that. Let's clone that page and let's clear it. So, for example, suppose you had the limit as x goes to pi over 3 of 7 times sine x. So, wow. Wouldn't that be a challenging lecture if all the stuff that the teacher writes disappears? That'd be like Harry Potter stuff, right? The limit as x goes to pi over 3 of 7 times sine x. So what I'm saying here is you could sometimes when you made all the little disclaimers, when all those disclaimers are checked, you could take the 7 and pull it out, and that would give you something like 7 times the limit of as x goes to pi over 2 or 3 of sine x. See, sometimes you could pull out that 7 and maybe simplify the problem a bit. Just focus on the actual part that's having that's changing, which would be the function. The constant is not changing, so it comes out of it, out of the equation completely. You could multiply when you're done with this part. This one you can actually do by plug-in method, or engineers, or any other things that we did. To get that's equal to 7 times sine of pi over 3, and then you'd be done with that. Okay, very, very famous. You could pull the constant so long as each of these pieces exists and is finite. So two super important. You got to prove the properties, and you got to figure out what they're good for. I'll give you a little tiny taste of what they're good for, but let me elaborate on that. So first, let's prove some of these properties. A couple of these properties I posted on the homework for you to prove. They're really nice problems. Probably the hardest one is the quotient or the product. To prove the limit of the product is product of the limits. That one is sort of challenging if you've never seen it before. And I put it on the homework, and I didn't post a solution for it yet, just on purpose, just to, you guys should think about it for a few days or a few weeks, and then we can talk about it. I'm not going to prove all of them here. Some of them I proved on the homework. Maybe I'll prove one of them here, and then we'll get a little taste of what they're good for. Okay, how does that sound? Let's prove one of the classic ones. The limit of the sum is sum of the limits, of course with a disclaimer, so long as each one exists and is finite. What exactly does that mean? Well, that means that we can assume that this limit exists and is finite. The limit of f as x goes to c is L, and the limit of g as x goes to c is maybe some other limit, maybe call it R, whatever. These numbers are finite. What we have to prove is that you could take this limit and distribute it. That's what we have to prove. Okay? So we have to get from this assumption to that result. This is our starting point. This will be our final point. When we get to this point, when we have proven that you can distribute that limit, we will be done. So often you can sort of narrow the gap. This is where the creativity comes. You've got to narrow this gap with logical steps, logical, infallible, logically penetrating steps until you make them meet and everything flows nicely. So the idea is to reduce the gap. We can often take one step backwards if we just make small little tiny steps. For example, here I could make the following step. I could say, you know what? If I'm calling this L and that calling R, really I just have to get from here to here, because from here to here will be a simple step. It's just a substitution of that and a substitution of that. Right? This narrows the gap a little bit. But it gets better than that. You can narrow the gap here because to get to this point where anytime you got to prove that the limit of blah is equal to some other stuff, all you got to prove is that their distance between them is smaller than epsilon, and that you can prove it. You can find the exact time when that happens. So I've narrowed the gap again. But wait, there's more. You can you know that f is getting really close to L and g is getting really close to R, because that was the assumption. So I regrouped these using just simple simple algebra, and distribute this minus L minus R, and put the minus L next to the F, and put the minus R next to the G. And now look at me. All I need to do now is narrow a smaller gap. I gotta go from this assumption to this conclusion, and seems like an easier task. But the way to get there is a secret ingredient. The secret ingredient comes from algebra or vectors, and it says that it's called a triangle inequality. It says that every time you've got, I'll give you the roots of it come from vectors. That's why it's called triangle inequality. And here's the root of it. Suppose you have some vector. You know, vectors have direction and magnitude. If you have some direction here, vector A, and you have some other vector here, B, and you have the resultant vector, the sum of them, and we have the sum of them. I'm just kidding, trying to cue this thing up. So let's compare. Let's do some simple common sense things. Suppose this is vector A. Suppose this is vector V, and suppose this is the vector. Well, not suppose. This is, by putting them end to tail, this must be A plus B, the vector. Now, if you were just looking at their magnitude, pretend this absolute value represents the magnitude, which means the size of the vector. Which vector would have to be bigger? A plus B, this vector, the magnitude, or the sum of these two magnitudes? This statement is talking about the magnitude of the green one and how it's compared to the magnitude of A and the magnitude of B. If you look at it as magnitude of vectors, it's really obvious that the longest one cannot be longer than the sum of the shorter ones. Or, so differently, that the longer one in magnitude has to be smaller than the sum of the other two. Because it's a triangle, that's why it's called a triangle inequality. And so I'll let you guys think about that. Actually, it would be a fun proof to prove that inequality. If you guys have a little extra time, I invite you to prove it rigorously. But here's a picture of it. I'm not going to prove that because it'll take me into a tangent. But don't get me wrong, I love proving things. I would prove that one for free. But I don't want to digress. That's the secret ingredient here that I need to fill in the gap. So here I go. I'm going to fill in the gap. You ready? I made the gap a little bigger because I have to write on it now. But don't worry, you're in good hands. This is where I'm at. This is where I got to go. What's going to go in here is I'm going to make use of that secret ingredient, right? The triangle inequality. So here we go. I shall go in yellow. So since the limit of f as x goes to c is L, then for any epsilon over 2, for example, by the way, this is a symbol that means for any epsilon over 2, there exists, this is a symbol for there exist, in case you don't know, there exist. For any epsilon greater than over 2, there exists a delta, a real number delta, greater than 0. I'll call this delta 1 because I don't want to get it mixed up with, I'll call it delta for L, such that if x is less than delta for L and not equal to C, this means not equal, so it's got to be, the distance have to be greater than, then what can I say, then the distance from f of x minus L, the distance from f of x to L is less than epsilon over 2, right? I'm just making use of this password. This is the definition for any epsilon, or epsilon over 2 or epsilon over 100. It doesn't matter. If epsilon is a positive number, dividing by 2 is not going to change that. So for that, there will also be a delta, such that being delta close to C guarantees f is epsilon over 2 close to L. The same thing I'm going to do on this side over here. So that one I'll do, say, in blue, whatever. For any epsilon over 2, there exists a delta for r. This might be a different delta, a delta for r greater than 0, such that being delta r close to C but not equal to it guarantees that my g of x will be epsilon over 2 close to r. You say, what? How's that going to help us? Well then, look at what we can do now. Oh, I need more space here, so I'm going to move this down. Then I come back over here. This is fun, huh? So then I have, look what I have here. F of x minus L. So then I choose the smaller of the two. If I'm close to delta 1, this is true. If I'm close to if I'm delta L close to C, this is true. If I'm delta R close to C, this is true. So I choose the smaller of the two so that both of these conditions are met. Then this will be smaller than epsilon over 2, and g of x minus r will also be smaller than epsilon over 2. Then you add them and you say you have the f of x minus L plus g of x minus r is smaller than epsilon over 2 plus epsilon over 2, because this distance is smaller than epsilon over 2 and this one's smaller than epsilon over 2, so the sum of these two will be smaller than the sum of these two, which of course is equal to epsilon. And now you see why I had chosen epsilon over 2. After all, I could choose any epsilon. If this had been 3, I would have chosen epsilon over 3. Anyways, but because of the triangle inequality, the triangle inequality said that if you have absolute value of blah plus the absolute value of blah, that one is always bigger than if you put them on their one absolute value. So that's exactly the game I'm going to play right here. I've got the absolute value of blah and the absolute value of blah. Let me give you more view here. I got the absolute value of blah and the absolute value of blah, and so by triangle inequality, this guy right here is smaller than f of x minus L plus g of x minus r. I've put them in, this whole thing is like A and this whole thing is like B. I put them into one absolute value, and that's when you put them under one, you get something smaller by the triangle inequality. But now look at the sequence of reasoning. This guy is smaller than that one, and that one is smaller than epsilon. So therefore, f of x minus L, therefore f of x minus L plus g of x minus r is smaller than epsilon. And I've done it. So long as my delta will be, I'm going to let the smaller of the two, this is the way you write a minimum of delta for L or the delta for R. I choose my delta to be the smaller of the two. And if it's smaller of the two, then both that's satisfied and that's satisfied. Then when I add those two together, I'm adding something that's smaller than epsilon over 2 plus something that's smaller than epsilon over 2. So total of sum of these two is less than epsilon. Use a triangle inequality to put them under the same absolute value. Voila! This is exactly this line, and we have proven that the sum of the limits, when each of them exists and is finite, is exactly the limit of the sums. Beautiful, huh? This is a sort of flavor that you could take for a lot of these proofs for the limits. And so that brings us to, of course, the famous questions. We got to prove all of them. You got to make them your own, and you have the most powerful tool at your disposal. That is the definition of limits. Super powerful. It helps you prove all these properties. And I've given you a little taste of what they're good for. Maybe we can do one more of these. What it's good for. Let me pause this. So last time, we've been doing the limits for a while now. We've been doing the plug-in method. The plug-in method would tell you to find this limit as x goes towards 11. All you do is plug it in there. If you don't get an indeterminate, you're done. But we never really got around to putting that in really firm terms. We now have the really powerful tool, the limit properties, which can be proven very rigorously using epsilons and deltas. And we're going to use that to see why that plug-in notion was actually grounded on very firm ideas. We can prove that now. Watch this. We're going to use the limit properties. Whoa. Let's do it. So here we go. Here's the proof. The limit as x goes to 11 of 3x plus 1 is equal to the limit as x goes to 11 of 3x plus the limit as x goes to 11 of 1. Why is that? Why? Well, that's because the limit of the sum is equal to the sum of the limits. That's a famous property that says you could distribute this so long as each one exists and is finite, which they are in this case. You'll see in just a second. Now let's see. With this one, can I pull out the 3? Can I pull out the 3? And the answer is yes. We can pull out the 3. And we know exactly why. This part I'm not going to do anything. So it's just limit as x goes to 11 of 1. And the reason you can pull out the 3 is because of the pull the constant theorem. Or not theorem, property. We talked about that one earlier. You can pull constants. And then we have the limit as x of x as x goes to 11. We say that's equal to just 11 plus the limit of 1 as x goes to 11, and that's by the what is that by? That's by the limit of x property. At the beginning we talked about that one. But wait, there's more, and that's equal to 3 times 11 plus the limit of 1. Well, that's just equal to 1 as x goes to 11. Why is that? Well, that's a famous one, the limit of a constant. We talked about that one also at the beginning. And so you see, what we did before, very nonchalantly, we just plugged it in there, was really nice intuitively, and it's even nicer now because we see that it's grounded on very firm ideas. These are the limit properties, which are themselves grounded in very firm ideas, which is the epsilon delta definition of limits. We've already proven that one using epsilon deltas. And in the homework, you'll prove a lot of these other ones using epsilon delta. So this is tight stuff like you won't see anywhere else. And so it's nice to see the plug-in method. This doesn't prove all the plug-in methods at all, but it proves specifically here when you have a linear, term, some of the things you can do, and it sheds some light into why we could do the plug-in method sometimes. Okay, that was so fun. Let's try it again. So this time, let's do it. Let's do the product. Let's do a little product one here. The limit as x goes to infinity of x times the limit as x goes towards infinity of ln of 1 over x, right? And what am I using here? The limit of the product is equal to the product of the limits. Famous. But wait, there's more. Here, limit as x goes towards infinity. That's just infinity. The limit of ln of 1 over x, that's going towards 0 from the positive side, so that's going to be negative infinity. Whoa. Whoa. That's my whoa sign. This is totally illegal. You see, these limits do not exist. Well, they exist, but they're not finite. So you can't be playing this game. That right there is a problem. When the whole point of that little asterisk was to be careful. You can only play this game. You can't play it in general. You can't do it always, but you can play it so long as each of them is finite and exists, which doesn't happen here. So that was just a nice problem to show you that you got to be careful with the disclaimer, with the little conditions. Conditions have to be met. This one, let's see if this one works. Is that true or not? Let's prove it. Let's check. The limit as x goes to 7 of 5x squared plus 3. Well, that would be the limit as x goes to 7 of 5x squared plus the limit as x goes to 7 of 3. Why? What did I use there? There I used the limit of the product as product of the limits. Super famous. So long as each one exists and is finite, it's okay. I'm going to see right now if each one exists and is finite. For sure, this one I could pull out the 5 as x goes to 7 of x squared. I'm going to write the x squared as x times x plus the limit of 3 as x goes to 7. Then a question, what did I do here? I took this 5 and I pulled it outside. Is that legal? Yes or no? Why? Yes, by pull the constant there property, you can do that. But wait, there's more. Could you take this limit and distribute it into each of the x's and say, hey, this is the limit of x as x goes to 7 times the limit of x as x goes to 7. Well, if each of these exists and is finite, yes, that would be legal. And we have reasoning why that's legal. Because of the limit of the product is equal to product of the limits. Oh wait, over here I think I said it wrong. When you take this, it was the limit of the sum is equal to sum of the limits. I was just testing you guys, see if you're paying attention. This is the sum. Limit of the sum. Okay, I'm just trying to get a good variety here, using all my properties. It's working good so far. So this is just the plain limit of x as x goes to 7, so that's just 7. Same thing there. This is just a 3, so I used a couple of things here. I used the limit of x, that's how I got the 7, and I used limit of the constant, that's how I got the 3 there. Limit of constant there's no x there, so it's not changing, so as x goes to 7, the limit is still 3. And that proves it. This proves what, our prediction before. Using the plug-in method, we would have gotten this answer, and this is a way of grounding it on very, very solid terms. Ultimately on epsilon delta definitions, which are very, very firm. Okay, alright, so maybe one more time. You could use it to prove this famous property even for a generic function, so long as you've got this disclaimer here. The limit has to exist and is finite. But if it does, then you could prove it generically that if you have a square of something, you can take the limit inside and leave the square out of it until you're done with all the limit work, and then put this square whatever your answer was. You can easily prove that. That would be, let's start off with that side. That is equal to the limit as x goes to c of f of x times f of x, and at that point all I'm using is just the definition of exponents, meaning that square right there means write it 2 times. And at this point I use the limit of f of x as x goes to c times the limit as x goes to c of f of x, and that I'm using the limit of the product is equal to product of the limits, and I'm using it correctly because I'm assuming that each of them exists and is finite. Otherwise this whole thing doesn't work. And then of course you have the limit of f of x, whatever this is, times that's the same thing as saying that the limit of f of x as x goes to c squared, because I've written it 2 times, and so that's just by exponents, definition of exponents. And so you see, you could take these careful steps and prove famous properties for generic functions. That's the power of the properties. Properties are super important, super famous. And so I hope that helps us address the two important questions. Prove the properties. We proved one here. We proved two more in the homework, and the other ones you should prove for fun. What are they good for? Well, they're good for a lot of things. They're good, for example, to verify limits. Sometimes they're good to verify why the plugin works. And you'll see more as we go on. They're good for breaking up complicated problems into smaller pieces, etc., etc. What do you guys think? Should we kickstart this? Alright, we'll see you guys here. Peace.